Great. Thank you so much for the invitation. It's, I don't know what counts as an old joke now the pandemic is 8 months long already, but I was about to say it's nice to be here with you in my living room, but I say that every time I give a talk. So anyways, it is nice to be here. Um, Everything I'm going to say is joint with Jonah Gaster, and I want this to be fairly informal. So I don't know people's backgrounds, so I'm going to try to keep things as simple as possible, and people should feel free to interrupt me if there are questions at any point in time. Okay. Great. So for the setup, I just want to start with some surface S. So let's say not necessarily closed, but let's say genus, uh, let's say G bigger than or equal to 2, just to avoid annoying cases, although most of the assumptions I make are not necessary for the theorems I'll state. I just want to make my life simpler in this talk. Maybe some number of punctures. I certainly don't want to consider infinite type surfaces. So let's assume that the Euler characteristic is actually finite. But I have some surface, and maybe it looks like this. Okay, here we have it, and it's orientable as well. So there's some punctures and there's some genus. And so far, I'm only thinking of it as a topological object, so there's no metric or anything like that that I've equipped this object with. And the idea is, so the question is to formalize some sort of model for randomness in terms of taking homotopically non-trivial curves on the surface, and then to analyze the properties of that type of a curve. So what should be meant by a random curve. And once you answer that question, then what are the properties of that object? And what should it look like? And so here I'm really talking about homotopy classes of curves, not curves in and of themselves. So I have some, I don't know, some object that kind of twists and turns around the surface and does some interesting stuff. Who knows? It might have some, essential points of intersection that can't be removed, and that's a curve up to homotopy on this object. So in the theory of sort of random objects, this is sort of the first question you always have to ask is always this: what do you even mean by random? And then there's generally many different things you could mean, and then you pick one of those ways of actually saying what you mean for a particular reason. Maybe you have a motivation in mind for choosing that notion of randomness, and you go with it, and you see what you get. But before we land on the notion of randomness that will be in for the majority of the talk, I'll just maybe like give you an idea of another notion of randomness that we won't use, but just to drive home the point that there's nothing super canonical about our choice of a random model. We chose it because we had an application in mind, which I'll tell you about. But so here's one potential answer to the question. So one answer, at least to the bracketed part in blue, is we could take our surface, because of the assumptions on the topology we made on the surface, there's going to be Riemannian metrics on this surface of constant curvature equal to -1 that are going to be hyperbolic metrics that are complete, that you can equip this surface with, and we can pick one. So choose a hyperbolic metric. And pick your favorite point on the surface. So pick a point X. And then what I want to do is just sort of pick kind of uniformly at randomly and I won't be super formal about what I mean by this, a tangent vector at x, and then just flow in the direction of that vector via the geodesic flow that this surface has once I equip it with hyperbolic metric. So choose at random, and there's a natural finite measure on the set of directions at a fixed point. So I can actually talk about randomness in terms of measure theory there. A direction at x and flow forwards along a geodesic. And so if I do this, here's just another copy of the surface down here. Okay. Here's my point x. So now I've chosen a direction, and now I flow in time forwards using the geodesic flow, and I get some kind of complicated object. I'll cross over myself probably lots, and I come over here and I do other stuff. Who knows what you do? You're never like on the nose going to arrive exactly back at the point x. At least the probability of doing so is 0. But with very high probability, after some finite time, no matter what threshold you set, you pick some small epsilon, and you fix a little epsilon disk around the point x, then because of the negative curvature properties on the surface, the geodesic flow is well behaved, and in particular returns into small neighborhoods of any point infinitely often. So if I wait long enough, eventually, so lots of time, so time goes by. Oh, I didn't mean to still be in this color. Whoops. And then eventually I come back this way, dot, 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 and I arrive back inside of this very small epsilon disk. And then what I could just do is kind of just cheat and stop here and then just close up by a straight line path inside of that disk. And I get a curve now, which is not a global geodesic because of this sharp turn that I made at the end, but it's very, very close to being a global geodesic because for almost its whole life, it's acting like a geodesic. And then just for a teeny tiny little piece, it's not. But then if I were to straighten it out into an actual geodesic, it would be within a very small neighborhood of the original of this piecewise geodesic object that I just drew. And so by choosing different time cutoffs, I'm going to arrive back into this disk infinitely often. I can get a sequence of geodesics in this way, and I could choose this as being a model for what I mean by a random curve. Okay. And people do this, and people have gotten a lot out of this model for randomness. It's a very beautiful theory. You learn a lot about the theory of geodesic currents by working with these sorts of notions of randomness. And this story is actually not unrelated to what we will end up talking about, even though it's not the model that we're going to be using. So it's a very nice model, as I said. Maybe one, it's not a disadvantage. It's just a place in which the model is non-canonical. We had to pick a hyperbolic metric to run to get the whole conversation started. And there's an entire, of course, moduli space of different choices there we could have made. And the curves, the actual curves that you'll get will in general depend, if you're trying to answer, this part of the question, what these curves look like will certainly depend on the hyperbolic metric that you chose to get the conversation started. And that's not a good or a bad thing, it's just the reality. Okay. So the model that we are actually going to use is a more combinatorial one. So less based on the Riemannian geometry and more based on the group theory. Okay, so a second answer. It's also going to be non-canonical in some way. Just you're choosing where to pay the cost of not being canonical. And in the second answer, we are not canonical because we start the conversation by choosing a generating set for the fundamental group of the surface. Okay, so pick a generating set, let's say a finite, and let's also say symmetric, which means that I include an element and its inverse in the generating set whenever I include an element at all. Generating set of pi1 of the surface, okay? And then once I do this, I get a Cayley graph. So consider the corresponding Cayley graph, the associated Cayley graph. I should have called this generating set something, so I will call it capital S. And once I do that, I can call the Cayley graph something that refers to that generating. I shouldn't call it S, that's the surface. Let's call it, I don't know, sigma. So here I have the Cayley graph with respect to this particular choice of generating set. Okay, and then what I could do is just put a uniform distribution on the finitely many elements in this generating set. So if there's n elements in the generating set, I'm going to assign a weight of 1 over n to each of those elements. And now the Cayley graph with respect to that generating set has the structure. It's a regular graph with exactly, n edges around any given vertex. There's n of these edges where n is the size of the generating set. And what I'm going to do is starting at a particular base point, let's just say the identity element in the group, okay? I'm going to take a dice with n sides and I'm going to roll it. And whatever side lands up, I traverse that particular edge. And I move in this way. And what I'm doing is defining a random walk on this graph. Okay, so run a random walk. On this graph. That's my mom calling me. I'm going to ignore that for now. So I run a random walk on this graph, okay? And what I can do is let's let W sub n be the location of the walk after performing this this game n times, equals the location after n steps. Okay. So what is Wn? Well, it's a vertex in this graph that represents an element of the fundamental group. So Wn is in pi1s. But in particular, if I fix a, if I'm careful and I do things the right way and I, draw a picture of the surface and I pick a base point, then and I draw all the generators on my surface, then what I'm really representing is just a homotopy class based at that base point, which is actually not specified only by, well, it's over specified by Wn. Even just knowing the conjugacy class of Wn would be enough to pick out a curve as long as I don't care about base points on the surface. And so what I'm getting here is, again, a sequence of curves on the surface that are being chosen by a different notion of randomness, a more combinatorial one instead of a geometric one. Okay, and again, this point will be driven home throughout the talk, but the answer to this part of the question here will again heavily depend on the choice of symmetric generating set that you pick in order to start this conversation. I'm just reading this comment here. Interesting. Yes, that's a good point. Yes. And it will turn out that the theorems that I'll write down will be very insensitive to the choice of distribution that I make. There's actually two places, right, where I'm making choices here. It's how to assign weights to the generating set, but also the generating set itself. The theorems I'll write down will depend on the generating set, but not so much on the distribution. Okay, so as I said, you know, hopefully when you pick a notion of randomness, it's because you have some reason for doing so. And Jonah and I were really interested actually in studying certain homeomorphisms on the surface. And those are called point pushing homeomorphisms. So just a quick crash course for those who are less familiar with the mapping class group of a surface. So let's say I have a surface S, and let's say that it's of the form, this means genus G, and there's one puncture. Okay, so the mapping class group, which I didn't even define yet, the mapping class group of any surface, not just of this one, is the set of, it's the group of orientation preserving homeomorphisms of the surface after I mod out by isotopy. And then there are some subtleties when you consider, subtleties when you consider the possibility of boundary components, which I'm not doing in this talk. So it's exactly what is written here. Okay. And it turns out that there is a very beautiful algebraic way to relate the mapping class group of a surface of genus G with one puncture to the mapping class group of the closed surface with no punctures. And so this is really, I guess, goes back to Berman. It's called the Berman exact sequence. And what it says is you get a short exact sequence. And what it looks like, whoa, I don't know what I just did. Maybe I can make that go away. Yes, okay, good. So it looks like this. I'm going to leave that blank for right now. This goes into the mapping class group of the surface of genus G with one puncture. This comes down to the mapping class group of the surface of genus G with no punctures, and then I go down to one. And I left this blank because I wanted to be theatrical and write it last. What is the kernel here of this map? It's exactly the fundamental group of the surface itself, based at the point which you're considering to be the puncture. So there's this translation you can make between punctures and marked points. So actually for this story, it probably would have been more clear if I was thinking of my punctures as just marked points. And then there's this one point on this surface that is special, it's marked, and on this surface, no points are special. And the marked point maybe is called X, and the fundamental group in this short exact sequence is based at that point. Okay. And the way to think about, well, one way to think about this is what you could do is if I have, really what's happening here? What's happening here is if I start with the surface of genus G in one puncture, what I could always do is just fill the puncture in, or if I'm thinking about marked points, forget that special point and just consider it as the rest of the points. And then the question is, which homeomorphisms on the original surface become trivial after I do this? And that's kind of the question that you're asking when you look at a short exact sequence like this, because this map here is coming from that forgetful map that just forgets the puncture. Okay, and these are exactly the point pushing homeomorphisms. So a homeomorphism, or really, I should say, if I'm being careful, an isotopy class of homeomorphisms is point pushing element of the mapping class group of the surface of genus G with one puncture means it's in the kernel of this forgetful map. That's a correct and not very satisfying way to define what a point pushing map is. It's always easier just to see a picture. Okay, so which I'm going to be horrible at drawing. They're not easy to draw. But the idea here is what you can always do when you have a puncture is I can take that puncture and I can take my finger and I can actually kind of push that puncture with my finger around a closed loop on the surface and come back. And if I do that, then the puncture hasn't moved at the end of this motion. It's back where it started. And I imagine that the surface is sort of made of like a very malleable material, or like water even. And as I'm literally pushing the puncture around this loop, I'm physically dragging the material of the surface with me along the way. And so if I imagine like maybe here is like a little piece of my surface, and let's say that this red curve is the curve in the surface that I've elected to drag the puncture around. So when I'm doing the dragging motion, so I'm dragging, when the arrows arrive at this black curve, the black curve is going to come with me. So now this kind of looks like this, and it kind of goes like that. And everything in the surface is getting dragged with me until eventually I land back at the puncture. And once I get to the puncture over here, everything that I dragged with me, I make go around the puncture like that. And so now the idea is the original black curve and the new black curve are not homotopic to each other, usually, on the punctured surface because of the presence of this marked point. But once I forget the marking, then they are homotopic. So there's no interesting action on the set of curves, and you're just getting a trivial map. Okay. And because I can choose any loop I want on the surface to do this around, I exactly get an entire fundamental group's worth of choices. And that explains the presence of this term in the short exact sequence. Okay. Again, I don't know people's background, so I'll try to be slow. In the mapping class group, there's a fundamental trichotomy that explains the behavior of different sorts of elements. So this is called the Nielsen-Thurston trichotomy. So Nielsen-Thurston classification of mapping classes. And I'm not going to be very careful here. You have three types. You have finite order ones. You have these maps that are not finite order, but sort of everything interesting that they're doing is happening on a subsurface, a proper subsurface. And then you have the most interesting case, which are the pseudo-Anosovs. And the idea of the pseudo-Anosovs is that they really mix up the surface in every possible way. They have very interesting dynamics. Okay. So the question is, are there any pseudo-Anosovs in the set of point-pushing homeomorphisms? And the answer is yes, there are lots of them. I think this theorem, I believe this is due to Krah, who first observed this, that a point-pushing homeomorphism is pseudo-Anosov if and only if the curve that you chose to define, this red curve that's associated to the map, fills the surface, which is to say that no complementary component of the curve has any non-trivial topology. So the defining curve is filling. Cutting along that curve, when you draw it in minimal position with itself, decomposes the surface into a union of disks, or maybe one of those disks actually contains the puncture, but that's it. Okay. And sort of the jump off point for our investigation, Jonah and I's, is this theorem due to Spencer-Dowdall. So once we know something like this, that the pseudo-Anosovs that are point pushing are characterized in terms of a topological property of the curve that you use to define the map, you can then ask all sorts of interesting questions. Like, pseudo-Anosovs have invariants that you can discuss, such as like their dilatation or their translation lengths on various graphs or spaces related to the surface. And you can ask, are there any relationships between the dynamical invariance of this pseudo-Anosov and topological properties of the curve that defines it? And so Dowdall, what he did was to define, he related the dilatation of the pseudo-Anosov to the number of times that the defining curve crosses itself when you draw it in minimal position. So if gamma is a filling curve on the surface of genus G with one puncture, then we have the following inequalities. Well, first let me add some more notation. Let's let, I don't know, like P sub gamma denote the corresponding point pushing homeomorphism in this mapping class group. Okay, then we have the following inequalities. The dilatation of the pseudo-Anosov is bounded above and below in terms of the self-intersection number of that curve gamma. And the bounds are as follows. It's bounded above by 9 raised to the power of the self-intersection number, and below by like the 5th root of that intersection number, more or less. Okay. So I think it's an interesting result because it relates dynamics to topology. You'll notice the large size of the gap here between the upper and the lower bounds. And that's for a good reason. I mean, Spencer works hard to get this bound. The lower bound is much harder to get than the upper bound. And the idea that what becomes very difficult to do is it goes back to Thurston, that you can kind of estimate this quantity by taking any simple closed curve on the surface and studying its iterates when you apply the pseudo-Anosov. You look at where it goes, and then you measure the intersection numbers between iterates of this curve and the original. And then if you normalize this in the right way and take a limit, you can estimate the dilatation of the map. Okay. But the problem is that when you write down a curve on the surface that fills the whole surface, it looks very complicated. There is a way that you can literally draw the image of a curve under point pushing by that curve. You just kind of drag it along. The picture is going to look very complicated, but you can do it. What becomes hard to keep track of is whether or not these iterates that you're drawing are actually, in minimal position with the curve that you started with. Like, you might be forming bygons all over the place, and then it becomes very hard to like measure intersection numbers in the right way, and then the estimates kind of drop down in size, and that's why this lower bound is quite small. But Jonah and I were wondering, well, what if you like just choose a point pushing map at random? Like, are these issues that theoretically come up in Spencer's argument, will they arise then in the sort of generic case? So we wanted to study a sort of random model for a point pushing homeomorphism. And that takes me back to why we chose this combinatorial notion for randomness for curves, because what is the point pushing subgroup? It is pi1. So that's our motivation. If there are any questions, I'm happy to take them. And if not, I think I'll state some theorems.
I mean, a naive question would be, are there examples to indicate whether those bounds are good, or is this sort of the point of your project?
Great question. As far as I know, I certainly don't know of any examples that indicate the bounds can be improved. Maybe someone else, even in this talk, might be able to answer that question in a more satisfying way than me. But it's, yeah, I sort of thought of it as like one of these outcomes of doing random mathematics. Like it's hard to find an example, but then like the generic case is the example. Okay, so maybe one theorem, which I just said out loud anyways, in a coded way. I guess we're still writing it up, so now. So let's say you run a random walk on the surface group, and you interpret it as running a random walk on the point pushing subgroup of the mapping class group. So let's say PWN be the nth step of a random walk on the point pushing subgroup of the mapping class group. Then, and by the way, I'm not being very careful. So first of all, and I'm being very uncareful because I didn't state one of my assumptions. With respect to, this is kind of crucial actually, with respect to the standard generating set. So in other words, you have, A1, A2, A3, A4, blah, 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 A2G, and then you have the standard commutator relation, okay? A1, A2, blah, 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 A2G minus 1, A2G. So I'm actually just drawing the standard generating set for the surface. This is actually a bit stronger than what we really need. We just need the generating set to consist of curves that are simple on the surface. This actually comes up in a kind of subtle way in the argument. But the standard generating set is good enough. Then we have the following bounds. The dilatation of this map, and again, I forgot to add in a clause, there exists some n, so that, and then I have the bounds I'm about to write down. This dilatation is bounded above and below by functions of the form e to the n square root little n, and below by e to the root little n over capital N.
So Tarik, somewhere in here, are we either assuming or proving that generically PWN is pseudo-Anosov?
Oh, good question. That's a great question. Yeah, I should have said that. You're right. So this makes no sense as written, because I've assumed that it makes sense to talk about dilatation for an arbitrary element of the point pushing subgroup, and it only does for the pseudo-Anosov ones. So what I should say here is this. So I'll say note. Note. This statement is sensical because it's already known that, and by the way, I'm being very sloppy here. So what I should say here is with probability converging to 1 as n goes to infinity. Now it's a complete sentence. Okay. And now in the note, I'll address Ty's question. The only reason why this statement makes sense is because it's known that PWN is pseudo-Anosov with probability converging to 1 as n goes to infinity. And that's due to a number of people. I suppose it's certainly covered by work of Maher and Tiozzo, who sort of wrote one of the central papers on performing random walks in hyperbolic settings. So on hyperbolic groups, on spaces upon which groups that satisfy very weakly hyperbolic assumptions act on. Okay. So in other words, you might interpret these inequalities as only making sense with high probability, because when PWN is not even pseudo-Anosov, we're not saying anything. But when it is, we're saying this. So there's still a gap, of course, because this capital N is in the argument of the exponent, but it's, heuristically, we're getting, e to the root length of the walk as an upper and a lower bound. Okay. So this theorem comes as a consequence of understanding other sort of basic topological properties of the random curve that defines the point pushing map. And I want to talk a little bit more about that. And then maybe if there's time, sorry, I should know this. Is this an hour-long talk or is it a 50-minute talk?
Yeah, aim for 50 if you can, but there's a tendency for people to run over, so we won't hold you against it.
We'll aim for
we won't hold it against you.
We'll aim for 50. Okay. So what I'll do now is I'll state a couple more theorems, or maybe just even one, and then I would like to give you an idea of how the first theorem follows from some of the other theorems I'll write down now. And we won't have time to get into the proofs of these other theorems. So theorem 2 is, let's say now we're running a random walk. Again, same people. Okay. So let Wn be the nth step of a random walk on pi1s. Again, with respect to the standard generating set, I'm not being careful about specifying the distribution, because the results aren't very sensitive to that anyways. But if you want, just imagine that I'm putting a uniform distribution on this generating set. Okay. Okay. Then there exists some n so that with probability converging to 1 as little n converges to infinity, we can bound the self-intersection number from above and below by square roots of the size of the walk. And so these square roots are exactly where these square roots come from in the first theorem. And again, I'm being quite informal. It's probably not the same capital N for both theorems. There is a single capital N that you could, at the end of everything, define to work for both, but the capital N that works for theorem 2 might not be the capital N that works for theorem 1, the minimum capital N. Okay.
And, I have a small question. Do you know, suppose you fix the element of a fundamental group and you choose your generators, you integrate over moduli space, right? So for every hyperbolic surface, you will have a geodesic, which will have a bunch of self-intersections, but you put some sort of reasonable measure on the moduli space, integrate respect to that measure, then probably you will, the actual geodesic on that surface will have self-intersection number comparable, but then when you integrate, you will come up with some constant. Does it seem natural or not?
I want to understand your question. Maybe if you repeat it, I will understand it. I didn't quite get you towards the end.
You have a bunch of hyperbolic metrics on a given surface, right?
Yes.
So you look at the element of a fundamental group and then substitute those and then integrate over the moduli space.
I understand. So you want to deal with the fact that we had to choose a metric in that first model and you just averaged over the entire moduli space. Yeah, people have done this. Yes. So this begins to relate to like work of Mirzakhani and people who, I mean, yes, it is natural. You can do this, and sometimes these integrals have, very interesting interpretations in terms of measures that you can put on the space of projective measured laminations.
But the self-intersection number is kind of a piecewise constant function, right? So it's quite reasonable.
Right.
And so answer of some sort. So how?
That's a good question. The short answer is I don't know.
Okay.
That's the short answer. The longer answer is, first of all, there was a typo in when I first wrote the theorem down, so I changed it in the dark of night when no one was listening. There should have been a quadratic and not a square root. Okay. And the reason it's these square roots in the first theorem still do come from this, but there's just an algebraic substitution that has to happen to go from one to the other. Another thing that your question reminds me of is that when you fix a hyperbolic metric and you look at this this model that you're talking about that you would like to integrate over moduli space, and you ask, well, okay, if I fix a hyperbolic metric and I take one of these geodesics, one of these curves obtained by running the geodesic flow for a very long time, what is the relationship between length and self-intersection? What would you expect it to be? You expect it to be exactly like this, in fact. The length and the self-intersection should be like a square of the length. That's what you would expect. And this follows from thinking about how the Liouville current behaves on that surface, and the fact that when you are choosing longer and longer, when you're choosing to follow the geodesic flow for longer and longer periods of time, with high probability, you're converging to this unique geodesic current on that surface called the Liouville current. And so you can relate self-intersection properties of that curve to self-intersection properties of the current that you're approximating better and better. So what one moral of this theorem is that the combinatorial random model is behaving in a similar way to the geometric random model before you integrate. So if you take some integration, if you integrate over the whole moduli space, I'm not sure what happens or how to interpret this function that you would get. It's this constant that you would get. I just don't know.
Okay. Thank you.
Mm-hmm. Okay, so I have 2 minutes, and so maybe what I'll do is just say out loud a few words about maybe one more theorem and how they relate to each other. Again, same people, same time, okay? Same setup as theorem 2. So same setup as theorem 2, okay? Then there exists a compact subset K of Teichmuller space so that with high probability, with probability converging to 1 as n goes to infinity, the metric minimizing the geodesic length of Wn lies within K. So again, there's a companion statement here that's required in order for this sentence to make sense. It's very much like Ty's question above. How do I know that there is a metric that minimizes the geodesic length of a given curve? So this goes back to work of Kirchhoff, that a metric is a curve is uniquely minimized in its geodesic length on a particular point in Teichmuller space, if and only if that curve fills the surface. So again, by using Maher and Tiotzer, you know with high probability that Wn will fill the surface. And so this sentence makes sense up to for getting smaller and smaller probabilities as n goes to infinity. Okay. So I guess it's time. I said I was going to say a little bit about how these theorems relate to one another. In particular, I would have liked to say a little bit about how theorem 2 kind of follows from theorem 3. I didn't get there, but I'm happy to say more about it if anybody's interested. And yeah, I'll respect people's time and stop there and thank everyone for their attention.
Okay, well, thank you. A particularly unimaginative question: how does theorem 2 follow from theorem 3?
Sure. So the idea here is one of these two bounds in theorem 2 is kind of immediate, and it's this one. So that's kind of obvious. If you just sort of take a picture of the surface, and you have a point here, and you draw the standard rows on the surface, then if I have a word of length n on this rows, then I'm returning to this point exactly little n times. And every single time that I return to this point, I might cross over previous strands of myself, and I might not. But the number of strands that have already existed before I've gotten there are n-1. So you get this kind of product, n times n-1 times n-2, blah, blah, blah. So that's where this bound comes from. this bound is where theorem 3 is actually useful. And the way that it works is to assume that it's not true. So proof by contradiction. Let's assume that with high probability, the self-intersection numbers are actually growing at a slower rate than quadratic in the length of the walk. Well, if that's happening, then what I could do is I could consider gamma, which is a curve. Oh, and sorry, this theorem here, there should be little n's, right? They're supposed to be the parameterized by the walk, of course. What I could do is consider gamma n, and I could divide it by n. So what does that mean? I'm treating gamma n now as a current on the surface, which one way to think about it is it's a measure on the right kind of a space, and so I can scale that measure down by n. And Bonahan's theory of currents tells you how to think about self-intersections of these weighted objects. And if I know that the topological self-intersection of this curve is growing slower than quadratic in n, this theory of intersections between currents, it's bilinear in the two arguments. So these little n's can factor out to give me something divided by little n squared, and this would have to go to 0 because I'm assuming that the curve itself has a self-crossing number that's growing slower than quadratic in little n. And what that means, if you think about it, is that this gamma n divided by n is converging to a lamination on the surface. It's converging to something that doesn't have any self-intersection at all. Laminations are not there. You cannot minimize the length of a lamination in the interior of Teichmuller space. Their length minimized on the boundary. So once you know that with high probability, your length is being minimized inside of some compact part of Teichmuller space, there's your contradiction.
Are there any other questions?
So Mirzakhani had a result that something about the thick part of moduli space, right? That as genus goes to infinity, probably going to 1, short geodesics are bounded from below, and so on and so forth. So in theorem 3, do you think, or maybe you can prove it, that this compact region, the measure of the compact region in theorem 3 goes to 1 as genus goes to infinity?
No, I think theorem 3 can be strengthened to there exists a point in Teichmuller space instead of there exists a compact set in Teichmuller space. I just can't prove that version, so I didn't write it. But heuristically, the metric in Teichmuller space that length minimizes curves along this walk should be the metric in Teichmuller space that length minimizes the rows that you chose in the very beginning in order to set up the entire model.
Okay.
And that last statement is not something that people have thought about before. It just seems like it's got to be true, right?
Yeah, not that I know of. Yeah, and I mean, the argument has some twists and turns for proving theorem. Which one is it? For proving theorem 3, which is why, I mean, yeah, we don't have that statement. What we can say is you can't get too far away in any honest metric on Teichmuller space from that unique metric if you want to minimize these curve lengths.
Do you construct K by taking a closed ball around that point?
Yes, exactly.
Yeah.
Well, if there are no further questions, let's thank Tarik again.
Thank you. Thanks for the invitation.